Hello everyone, I'm Lara from eProsima, and today I will host this embedded working group. As usual, write your name, please, on the attendance list in the document I'm sharing. And as a recap of the previous meeting, John Gentilin, principal engineer of Sony PlayStation, was here, and he talked about ROSbot with MicroPython. ROSbot is an autonomous open source robot platform based on ROS, and MicroPython is a complete Python compiler and runtime that runs on the bare metal. Also, Arnaud Tafenel, co-founder of BitCraze, were here too with a talk about Crazyfly. Crazyfly is a company focused on developing and manufacturing a small quadcopter called the Crazyfly. He explained the potential benefits of the new framework for projects like micro-ROS. And today, my colleague at eProsima, Antonio Cuadros, is here with me. Hello.
Hi.
And he will demonstrate an open manipulator X control approach by Renesas and eProsima using micro-ROS. And after, Daniel Selman from Elektro worker is here, and he's going to talk about micro-RCEDDS as an interface for drivers in amperes. Okay, so are you ready?
Okay, so let's go. Let me share my screen.
Wait, I'm going to.
Okay, we are good, right?
I think so.
Okay, so as Lara said, I am Antonio Cuadros. I work here in eProsima. I'm also one of the developers in micro-ROS, along with Pablo, who is also in this room today. And I'm going to present a demo that we have developed along with Renesas that has been shown in the embedded world a few weeks ago. I'm in fact going to start with a little video of the demo, so you know what we are talking about. Okay, this is Thomas, one of our colleagues in Renesas, and here is the manipulator that I will speak in a few moments, and everything here is running in micro-ROS. Okay, just to has a quick introduction to the demo. Okay, so let's continue. I'm going to start with Renesas and micro-ROS because we have quite an alliance going on between the two entities. Then I'm going to explain the use hardware on this demo, the demo architecture, and then I will make a small live demo here, the manipulator that I have set up right in this table. Okay, so Renesas. If you don't know Renesas is one of the global leaders in semiconductors and microcontrollers. They are in almost every field, like automotive, IoT, industrial. They wanted a bigger presence in the robotics field, and they saw in micro-ROS an emerging opportunity to merge the robotics with their actual microcontrollers from their own company. And they are, in fact, the official reference board from micro-ROS. If you go to our official page, in just a moment, okay. They are the recommended option, as we have worked a lot in the integration with the micro-ROS. They also have a support option when they are the most relevant board in micro-ROS setup. Okay, they are also quite powerful MCUs. This family is meant from IoT, but with micro-ROS you can also apply to robotics. Let me go back. Okay, so for the integration with the Renesas framework, Renesas has its own IDE called S Square Studio, which is based on Eclipse. We have integrated most of the capabilities they offer, like the different RTOS, bare metal, FreeRTOS, and 3DEX, and a different set of transports like UDP, UART, EISB, Wi-Fi, and the CAN-FD. And also we have put some effort in documentation, training, and demos. Like this, we have a set of videos on the eProsima channel where we show step by step how to accomplish a goal, from a basic publisher example to a more complex project like this one, where we control a motor through a CAN-FD transport. And everything is step by step, like the hardware explanation, how to integrate the micro-ROS in the IDE from Renesas, an explanation from the code to the actual representation of the demo, okay? In this demo, we have the motor actually moving, and it's represented in RVs. This demo from the manipulator is more or less the same. It's just a command sent to micro-ROS, and then the odometry is received and represented in RVs. Okay, Renesas. With Renesas, we have also included a hardware-in-the-loop test bench here in our office, where we have a farm of Raspberry Pis, which each of them has a ROS2 installation, and not the same. One has Humble, one other one has Galactic. This is quite interesting because this hardware-in-the-loop approach, the micro-ROS code is actually built flashed into the board, and then different transports can be tested against the real hardware, just like a regular user will use micro-ROS. So when we have a release or a new change, we can feel safe that everything is going fine through the test bench. Okay, now for the hardware. Renesas is developing what they mark as winning combinations that integrate their hardware with external software tools to offer a fast-to-market time. Okay, here we have a board designed to control motors and also be integrated with ROS. Okay, the board can control servos to a single-wire UART, and by your side we have a micro-ROS integrated in this board. So we make the bridge between those two and the actual motor control. In fact, this board has been shown here before in this embedded working group in a Turtlebot demonstration by Renesas, by a colleague of Renesas. And now the Open Manipulator, the manipulator that we use in the demo is the Open Manipulator X. It's quite known in ROS. It is open software and open hardware, meaning that anybody in their houses can print the actual manipulator with a 3D printer and build it. It is ROS enabled, but to communicate with ROS, you actually need a specific hardware or solution by the Dynamixel, the servos provider. That's the main advantage of micro-ROS in this demo, that you don't need any specific hardware. You just need to integrate micro-ROS in the board that you are going to use, and this way you can use the complete ROS2 toolset with this manipulator without any specific hardware or library by a supplier. Now for the demo. The demo is controlled with a gamepad, a regular PlayStation gamepad, which controls which sends its commands using the twist joy, which is a public ROS2 package. And then, well, these commands from the gamepad go to the board, which is running micro-ROS, obviously. This board then get these commands with a manipulator controller node. controls the manipulator movement and behavior. The odometry is retrieved from the manipulator and is represented in Arbis. I'm not going to be able to show it today because I'm having problems with my graphics cards, but we have a video where it is shown that I will show at the end. We have also included a watchdog for the communications, meaning that if the communication is lost with the micro-ROS agent on one on the side, the manipulator will stop its movement for safety measures. Okay, this is more or less the demo flow. On the start, the manipulator will wait for the agent to be connected, and once it is connected, it will start the automatic mode. In this mode, the manipulator will begin to move a set of blocks to one point to another. That's it. But we have also included a manual mode where with the gamepad we can control the actual movement of the manipulator, and then we can go back from one to the other. I will also show how the manipulator stops if the connection with the agent is lost. Okay, I'm going. Let's go. Can they see the manipulator with the camera?
Now you are sharing your.
Yeah, from your camera. Can you see it?
Yeah, okay.
I don't know if I.
Can you put the camera in the TV? Okay, I can see. Wait a second. I can see it.
I don't know.
I can see it right here. Okay, yeah. Well, fine enough. Okay, I'm going to start the gate pan bridge. Okay. We are connected. I'm going to power up the manipulator. Okay, right now the manipulator is waiting for the agent to start. I'm going to start the agent, the serial agent here. Okay, this is not connected. And
They are not seeing
they're not seeing the. Yeah, but they are, no?
No, yes. Probably.
Yeah, but from your camera they can see it. I mean.
Yeah, we can see it.
Okay.
Okay.
Okay, fair enough. So once I connect the transport, okay, everything is running right now, and the manipulator is waiting from the start order. Okay, I have to place this carefully. And now with the gamepad, the automatic mode starts. Okay, if I disconnect the transport, the manipulator will stop. And if I reconnect, it will go continue as usual. Okay, and now I can control the manipulator using the gamepad. Okay, I can try to catch a block here, more or less, maybe not. Okay, and then we can go back to the regular mode. And well, that's it, more or less. Okay. Now I'm going to show a small video that we made in our office, so you can see the actual Arbis representation. It's more or less the same that you have seen in the right here. Okay. The block stacking from one side to the other side. Okay, and there is Arbis. Okay, as you can see, we have included the blocks on the actual representation. It's the same. You can control the manipulator with the gamepad, play around, open the driver, closing it, and then going back to the automatic mode. And that's it for this demo. This demo has been on the embedded open world, and we know that it's going to be on different parts of the world by Renesas to sponsor micro-ROS around the globe. So if you have any questions, I can ask. I will be happy to answer them. And if no, I guess that's it.
No questions? Okay, so no questions today. Thank you very much.
Thank you.
Antonio, it has been a
Thank you for your time.
It has been a very interesting demo.
Yani şuradan aşağı atalım mesela. Yani o şu yukarıya işte böyle bir yuvarlak bir şey yapalım. Hayır. Yukarıdan verirsen robot
Elchin, are you asking a question?
No, I just thanks.
Okay. We didn't hear very well. Okay, so our next talker is Daniel Selman from Hanin Elektro. So, Daniel, are you ready?
Yes, of course.
Okay, go on.
Thank you, Lara.
Thank you.
So first of all, I will share my screen. Hope everyone can see my screen.
Yes.
For a second. Okay,
Yeah.
perfect. So hello again, everybody. My name is Daniel Simon. I'm a software engineer working for Hanin Elektrowerke. Hanin Elektrowerke is a company based in Germany and has 75 years of experience and expertise gained as a global specialist for customer-specific drive systems and components. And its product line ranges from AC to three-phase motors, linear actuators, frequency inverters, and fan drives through to pumps, drain pumps, and circulation pumps, for example. We do develop and produce high customized drive solutions worldwide based on the slogan Moving Ideas. And we have 5 highly specialized product divisions offer solutions for a wide variety of applications and industries. And what I will talk about today is first a new drive that we came up with. It's a gearless wheel hub drive designed for the use in autonomous mobile robots, AMR. Then we will discuss the opportunity to connect a drive to a DDS and our implementation of drives in AMRs. Then I will tell something about a drivetrain controller that can handle up to 4 drives and that is also connected to DDS, enabled by micro-XRCE DDS. And I will talk about benefits we see in a drivetrain controller. Yeah, and in the end, I will show you some results from our hardware in the loop simulation environment. So first of all, on the left side, you can see the drive we designed for robotics applications, especially for AMR and HEVs. And it's contemplated as a in-wheel drive. That means that the drive is inside the wheel. So this blue one is the wheel, and inside of the wheel there's a motor. Additionally, we implemented many different peripherals and components like safety brakes, or one safety brake that's a black thing at the end of the wheel. Inertial measurement units and some safety features implemented on the drive controller. That's the thing here on the bottom, below the motor. The safety features are STO and SPC. That stands for Safe Torque Off and Safe Brake Control. And we want to provide to our customers a system that can easily be implemented and parameterized, and therefore you need a suitable communication interface, of course. You need a well-defined documented protocol and protocol message data. Yeah, and the single components of the drive are modular, and most of them are optional and independent from each other. But a customer might need a way to get states or process data from each of the components, or a way to control them. So next slide will come. Yeah, there it is. Okay. So there are many different interfaces or communication interfaces you can think of when it comes to controlling motors or drives, like Modbus, CAN-open, or what we also often do is simply controlling by DIOs or analog interfaces. But now we have to consider which interface makes most sense for an AMR or other robotic applications, and therefore for our customers. So we have done research and had many conversations about that, and we think that DDS has benefits in terms of the abstraction level, the flexibility and so on, and the accessibility. And the thing is that today, when you take a look at different AMRs and the drives that's implemented in the or mounted at these AMRs are, there usually you would find so-called DS402 protocol. That is a standard CAN-open protocol stack for drives, which is widely used. We also use DS402 protocol for some products. It's pretty much state of the art. It's reliable, but we think that it's when different components, as mentioned last slide, are used, or if you can provide more complex or need to provide more complex information than just a rotor position or a rotor speed of a motor, then DS402 would lead to large lists of parameters, and that's where we think that that DDS can do better. So because we want to do some pre-processing and provide more complex data to achieve the goal of easy-to-use plug-and-drive system for AMR. So what are the advantages of a micro DDS communication interface for a drive? I've been talking about the different drive-related components. If you think about the battery, for example, there might be a battery management system on an AMR. And this one might be connected to our drives with some kind of communication. So what we can do is publishing information about a battery over DDS. Another example is the drives and the IMU states that can be used to calculate if the system, for example, is standing, has a safe stand, or maybe stands on a sloped plane. So also it can enable the brakes automatically and publish this information to a potentially mounted cobot via DDS. So also we are able to publish wheel odometry data by using the IMU and fusing the sensor data. We have real-time capabilities in our drive controller, of course, and that's how we can pre-process highly precise information about how fast the wheel is going, not just spinning, but it's moving in space. So another thing is time synchronization. That's a big benefit we can make use of. For example, if you think of failure management or something, that can help you to do better analysis to the fault history and the reasons for failure that possibly can occur. So all the implementation of a micro DDS interface in our drives has many advantages. The biggest benefit is that DDS drive that the DDS gives great modular access to every drive-related component and complex data. So so far we've used many different standardized ROS2 defined DDS topics, mainly target speed values, of course, and some published states of the system, but also odometric data, and maybe sometimes the raw IMU data. But Hunning can customize topics of the drive system to your needs or to customer needs, of course. And until now, I was always just talking about a single drive system, which or with its features, components, and its capabilities, and so therefore a reasonable DDS interface. But in most of the AGVs, you need to handle multiple drives, of course. And the tasks and relations between those components are quite the same every time. So we have to think about the drive itself as a component of an axle, for example. So we had the idea of an intelligent drivetrain controller. We call it, in short, RBC, because it's a more common term you can find in the ROS world. It's a robot-based controller. It's quite a similar approach as Antonio presented lately. It's another embedded microcontroller-based system that controls the whole kinematics of an AGV and can therefore control 4 drives, and that has a micro XRC DDS implementation. So with an RBC, now the drives itself are, if you want, so a component of a differential drive maybe, or any other kinematics. And on the left side here, you can see the DDS interface. Here are listed only some movement-related topics, but you can think of any topic that makes sense for you. So we are using Ethernet UDP transport layer, and typically, we would publish data or subscribe to data at about 50 hertz, but that's just in the middle of there you can see the real-time control loop, and that is where the benefits of an embedded system come into play, because now we are able to implement trajectory following or control loops, other control loops, and an odometry observer. We are running these control loops usually at 1 kilohertz. And our software toolchain, maybe some words about that. We are using a Simulink toolbox to build our control model, the observer, and so on. And that's because just coding such complex control loops that can be or is very hard, especially hard to debug. And we have built our own robotics toolbox, if you can call it like that. It's like an extension to our toolbox that we are using for controlling our drives. So this control loops and observers need many data from different peripherals and components like the IMU or the drives. And that's what you can see here. It's a CAN interface, an SPI interface, and maybe something else. And here you can see our RBC, or Intelligent Drivetrain Controller. and our drives in an AMR system environment. Also, our you can see the safety monitoring device that has, in this case, not a certain or decent communication interface, but maybe a safety PLC could have, and then you would also connect this device to a robot-based controller, and therefore you can achieve some benefits or something. So you can see that we can choose between different transport layers. In this case, a communication to the drives is yet an open communication between the RBC and the SMCs. The interface between a battery management system and maybe a here not shown lifting system or handling system or something can also be realized. Yeah, all of these implementations are processed in, if needed, so real time, of course, and being published to a DDS system where the micro DDS agent is running. So being able to implement the line following or trajectory following algorithm or the odometry observer, we need to subscribe to different topics. First, you need to you need information about the global position of the system. Normally, a customer would use the SLAM algorithm for that, running on a navigation system you can see here. I've seen in similar concept that the micro-XRCE agent is running on a navigation PC like that, and that seems to be a requirement for an architecture like that. We are using our own method that can calculate a trajectory segment simply by subscribing to a so-called look-ahead point. A look-ahead point is a point or pose that lies on the path, and if you want to know more about look-ahead points, maybe you can do some research about the pure pursuit controller. It should be, it's widely known, I think. And the odometry that's being calculated on the RBC is yet very precise because of a certain IMU on the RBC and a sensor data fusion running on that system I've mentioned so far, and it can still be optimized when using our wheel drives, because, as I said earlier, the drives can calculate their own odometry. In other words, the speed at which they are moving. So in the end, we have a system that's much easier to implement, which inherently brings functionality like odometry, observer, and trajectory following, and of course some other possibilities like controlling the system with a command velocity manually. And all in all, it's customizable and that's very good performance. Better than running all of this maybe on a navigation PC. And all of this is enabled by the opportunity or the possibility to run a DDS on a microcontroller with real-time capabilities. So in the end, I would like to give you a short impression of how we are testing our RBC. Of course, it would be dangerous to just do all the testing on a real system, of course. Our drives are capable of carrying 500 kilos now, and yes, that can be a lot of power. So all of the drives and the kinematics and physics is simulated on a PC, so a simulation PC, and this is communicating via DDS to the RBC. I've seen now that it needs to be XRCE DDS agent, of course. So the simulation environment is a result of a cooperation with different universities, and so far we have been using Weeboards as well as Gazebo. And of course, in a simulation environment of this size, where we need to transfer many data, just think of the IMU data that needs to be transferred from the simulation PC to the robot-based controller to be fusioned by the observer. That leads to some stability issues. And yeah, that's my last slide. There are two main parts we're working on currently. First, the parameterization. We are looking for a good way to send and receive parameter values over DDS. Of course, in the ROS world, there are some topics we want to use provided by the ROS client library. But at that point, I have to mention that currently we're very happy just using micro-XRCE DDS and not the whole micro-ROS implementation. Yeah, second, we are wondering if there's a good way of implementing a command and status interface. Of course, sounds simple, and there are simple ways to just transmit a 8-bit value like another communication standard, but maybe it can be more advanced to transmit a string value as a command word, because yeah, maybe you can directly interpret this, or it's directly interpretable by the user. Yeah, and we should, of course, in terms of command interfaces, should think of good quality of services. Recent current problems we have, with sending, receiving large data in terms of embedded systems. Of course, we wanted to receive path data with about 1,000 or 4,000 or more poses. Yes, we know that this usually works, but we just need some debugging to solve that. And last, as I said, when we want to run our hardware in the loop simulation, it often comes to stability issues. I think it's because of the high metadata traffic or something, but that's not a very big problem to me, I think. So, yeah, thank you for your attention, and I would be happy to answer some questions if there are any.
Yeah, thank you very much for this very interesting talk. And I have a couple of questions. And at the slide, unfortunately, I didn't see any slide numbers, so I just have to see where the slide is on our base controller you have introduced, where you basically had these three parts, micro DDS, then the control loop, and the periphery. And I was just wondering, this looks very similar to the ROS2 control framework. So is this the framework that you are using? Is this in terms similar to it, or is it something? Yeah, that would be my question. I mean, in the ROS2 control framework, they use exactly the same thing, that they have ROS subscriptions, and in order to achieve real-time control, they have outside of ROS2 a real-time thread,
yes,
which is running then with 1 kilohertz. So I was just surprised because I see here the same architecture.
Yeah, you are right. Thank you, Jan. It's quite the same tasks to do, like the ROS control framework, the ROS2 control framework. Yeah, so it's basically quite the same architecture. Yeah, but of course it's running on an embedded system, and communication is via micro XRCE DDS. Yes, so you can achieve the real-time control loop on an embedded system. That's one option you have. But if you want to use the ROS2 control software implementation, yes, you could use that maybe. But I think we've used it and tested that a few months, years ago maybe, and it's I think if I remember correct, it's a big yeah. It's a lot of effort to do to get that one running. Am I right? I don't know. It's quite complex.
Okay. And I have another. So when I understood you correctly, you're just using the XRCDDS client with micro-ROS running on this RBC, like you start the executor and all that stuff, or is this completely you're just having your real-time control loop there and
yes.
So I was a little bit confused when you say you're not using micro-ROS but only XRCDDS.
Yes, we are only using the XRCDDS client. You are not you don't have to use the ROS client, the micro-ROS library to use micro XRCDDS client. So
okay.
That's just the communication framework below the ROS2, micro-ROS2. So.
Any reason for that? That you say, okay, I want to use this protocol directly and not on the RCL or RCLC level, or for performance reasons, or was it all?
For now, there's no need for using the functionalities of the micro-ROS library. We are totally happy with all we can do with the micro XRCDDS client so far. Maybe one day, if it as you can, as I said, the parameterization interfaces could be one reason to maybe implement micro-ROS software, but or another reason would maybe be to have a server client topic or something.
Yeah. I mean, because then you can use parameters and services and everything, right? And just another question regarding real-time calculations. So, I mean, typically, your this real-time control loop runs at a very high frequency, let's say 1 kilohertz, and your data or let's say the goal where you move to comes from a planner or something with a much lower frequency.
Yes.
But sometimes the local planner takes maybe longer.
Of course.
And there's some, it does not always come with a fixed frequency, and that means, so to say, the real-time control loop basically expects data with a certain rate, but it's maybe not coming with this thing. So I was just wondering regarding the safety argument or the safety analysis of this. Is this somehow considered? Do you have then how do you deal with so the question is basically, how do you deal with latency issues that are coming from outside, where that the planner basically takes longer to send these messages, and then locally in the real-time control loop you're waiting for your new goal point, but you're not getting it, so you just continue on this, or is there some monitor or some to be on the safe side that you're not bumping into something? Or
Okay, yeah, thank you. First, I have to ask you, when you're talking about the local planner, do you mean the SLAM algorithm? Yes, or because the local planner for me is, for example, a pure pursuit algorithm, and that's totally real-time capable. And the SLAM algorithm isn't. That's totally correct. Yeah. So you have to find a way to have a very smooth but accurate position of the system, and you can achieve that by using a fusioning algorithm that fuses the data from the SLAM algorithm that gives a highly precise but at slow rate published data. On the other hand, we can use the odometry observer that we have implemented to have a high-pass filtered positioning system. So by fusing these both data, we can achieve a very precise but available at high rates position for the system, reference position. And yeah, the rest is just doing some coding.
Yeah, thanks.
Okay, thank you very much, Daniel. Are there any questions? Okay, so thank you very much for being here and for the talk. It has been very interesting. And for the rest of the attendees, also thank you and see you at the next month's working group. So thank you again and bye.
Goodbye.
Bye-bye.
Bye-bye.
Bye.